My sincere greeting to one and all. I am Tamanna from Basic Chemistry Honors Second Year. Today I am here with chapter Amines. Introduction. Amines are very important class of nitrogenous compounds which may be regarded as derivatives of ammonia in which one or more hydrogen atom have been replaced by alkyl or allyl groups. For example, methylamine, dimethylamine, trimethylamine. The number of hydrogen atoms that have been replaced serves on the basis of classification of amines as described below. Classification of amines. Amines are classified as primary, secondary, or tertiary amines according as one, two, or three hydrogen atoms of ammonia molecule have been replaced by allyl or aryl group as described below. Primary amines. These are the derivatives of ammonia in which one hydrogen atom of ammonia has been replaced by alkyl or aryl group. Therefore, they are characterized by the presence of amino groups. NH2 is linked to alkyl or aryl group R. If R is alkyl group, the amine is called aliphatic amine. If R is aryl, for example, amino group is attached to an aromatic ring, the amine is also known as aromatic or aryl amine. Amines in which the amino group is attached to an aromatic substituted alkyl group may be called as ara-alkyl amines. However, they are quite similar to aliphatic amines. For example, methylamine, aliphatic amine, aniline, aryl amine, benzylamine, ara-aline amine. Secondary amines. These are derivatives of ammonia in which two hydrogen atoms of ammonia have been replaced by alkyl or aryl groups. Therefore, they contain amino groups NH linked to two alkyl or aryl groups. If the two alkyl or aryl groups attached to nitrogen are identical, the amine is also called simple. If the two groups are different, the amine is termed as mixed. Again, the secondary amines may be purely aliphatic or purely aromatic or mixed aliphatic aromatic depending upon the nature of two groups attached to nitrogen. For example, dimethylamine simple and aliphatic, diphenylamine simple and aromatic, methylethylamine mixed aliphatic, and methylaniline mixed aliphatic aromatic. Tertiary amines. These are amino derivatives in which all three hydrogen of ammonia have been replaced by alkyl or aryl group. Therefore, they contain tertiary nitrogen attached to three alkyl or aryl groups. Like secondary amines, they may be classified as simple or mixed or purely aliphatic or aromatic or mixed aliphatic aromatic. For example, trimethylamine simple and aliphatic, dimethylethylamine mixed aliphatic, and n-dimethyl-aniline mixed aliphatic aromatic. Besides amines, there is no other class of compounds called quaternary. There is a class of compounds called quaternary ammonium compounds or tertiary alkyl ammonium compounds, which are closely related to ammonia. These compounds may be considered to be derivatives of ammonia compound in which all the four hydrogen of ammonium ion have been replaced by alkyl or aryl groups. For example, tetramethylammonium hydroxide, tetraethyl ammonium chloride. Structure of amines. The structure of amines and bonding in them is similar to that of ammonia. As in the case of ammonia, the nitrogen atom of amines is a state of sp3 hybridization, so that the hybridized orbitals are directed towards the corner of tetrahedron. There three of their orbitals which contain one electron each from sigma bond with the three groups attached to nitrogen, while the fourth orbital contains a lone pair of electrons. For example, the structure of trimethylamine may be depicted as follows: sp3 hybridized. Like ammonia, the actual shape of amines is pyramidal. The C and C bond angle between is very close to tetrahedral angle of 109.5 degree. The actual angle in trimethyl ammonia is being 108. The angle is slightly greater than NHH angle of 107 in ammonia due to the greater steric repulsion between methyl groups as compared to the hydrogen atom in ammonia. Nomenclature of amines. Aliphatic amines. Aliphatic amines are as named as follows. First, common system. In the common system, aliphatic amines are named by adding the word root amine in the word amine to the name of the alkyl group or group present in the molecule. For example, methylamine and propylamine, dimethylamine, dimethyl and butylamine. Second, IUPAC system. In this system, the aliphatic primary amines are named by removing the final E of the name of parent alkane by adding the suffix of amine. For example, methenamine, 2-propanamine, 3-methyl-1-butanamine. The secondary and tertiary amines are named as nitrogen substituted primary amines. For example, N-methyl-methenamine and N-dimethyl-methenamine. If the secondary and tertiary amines are mixed amine, the longest straight chain is taken as being to the primary amine. For example, N-methyl ethanamine. Ethanamine is the parent amine. The methyl group is the substituent of nitrogen. N-ethyl and methyl butane 1-amine. The butane 1-amine is the parent amine. Ethyl and methyl are the substituent of nitrogen. N-methyl hexane 3-amine. N-dimethyl pentane 3-amine. Sometimes, in the case of complex amines or amines having other functional groups of higher priority, the compound is named by prefixing the word amino or N-alkyl amino or N-dialkyl amino before the name of the parent compound corresponding to the longest possible chain. The position of the various groups along the straight chain are of course given in accordance with the journal IUPAC rules. For example, 2-methyl-1 N-methyl aminohexane, 2-amino-3-methyl butanoic acid. Aromatic amines. Aryl amines. The simplest aromatic amine is aniline. Even though its IUPAC name is benzenamine, it is popularly known as aniline. Most of the aryl amines, example, amines in which amino group is directly attached to an aromatic ring, are generally named derivative of aniline, although some of them are given special names also. Thus we have N-methylaniline or N-methylbenzenamine, N-diethylaniline or N-diethylene benzenamine, para-nitroaniline or 4-nitrobenzenamine, orthotoluidine or 2-methylaniline or 2-methylbenzenamine, para-anisindine or 4-methoxyaniline or 4-methoxybenzenamine, 2,4,6-trimethylaniline or 2,4,6-trimethylbenzenamine. Diaryls or triaryls amines, they are named in same way as aliphatic amines, either by writing the name of aryl group followed by the word amine or as nitrogen substituted primary amines. For example, diphenylamines or N-phenylaniline or N-phenylbenzenamine, triphenylamine or N-diphenylanine or N-diphenylbenzenamine. Side chain aromatic amines or ara-alkyl amines. The amines containing the amino group in the side chain are generally named by either writing the name of the aryl group or adding the word amine or as substituted alkylamines. For example, benzylamine or phenylmethanamine, beta-phenylethylamine or 2-phenylethanamine. salts of amines. They are named by replacing the words amine by ammonium, or replaced by aniline by anilinium, and they adding as separate word the name of the anion. For example, methyl ammonium chloride, diethyl ammonium acetate, aniline bromide. Preparation of anilines. On the several methods available for the preparation of aliphatic or aromatic amines. The important are discussed below. First, reduction of nitro compounds. The nitro groups can be easily reduced to an amino group either by catalytic hydrogenation or by chemical reduction. This method is very commonly employed for the preparation of primary aromatic amines. Since aromatic nitro compounds are readily available in recent years, the method is becoming increasingly important even for preparing aliphatic amines, since aliphatic nitro compounds are now being prepared commercially by vapor phase nitration of alkanes. First is catalytic hydrogenation. It is generally carried out by treating the nitro group compound with molecular hydrogen in the presence of finely divided nickel or platinum. For example, nitrobenzene plus 3 moles of H2 in presence of nickel or platinum gives aniline plus 2 moles of H2. But a serious limitation of catalytic hydrogenation is that the other reducible group, such as ethylenic double bond, is present in nitro compound also get reduced. For example, paranitrostyrene in presence of 4 moles of H2 and platinum gives para-ethyl plus H2O. Second is chemical reduction. Chemical reduction of nitro compounds is usually brought about by adding hydrochloric acid to a mixture of nitro compound and a metal such as granulated tin or iron. The aniline is obtained in the form of its salt, from which the free amines is recovered by the addition of alkali followed by steam distillation. For example, nitrobenzene in presence of SnHCl gives an amine salt. Then on steam with OH negative, steam distillation give aniline plus SnO3 negative. Paranitrotoluene in presence of FeHCl gives an amine salt, and then further on steam distillation it gives paratoluidine plus Cl negative. Lithium aluminium hydride can also be employed as a reducing agent in case of aliphatic nitro compounds. Note, if it is desired to reduce only one nitro group of a compound containing two or more nitro groups, the selective reduction can be achieved by using ammonium hydrogen sulfide NH4HS for example metadinitrobenzene in presence of NH4SH gives metanitroaniline. Second, reduction of nitriles. Aliphatic or aryl primary amines can be obtained conveniently by the reduction of nitriles. The reduction may be brought about a catalytic hydrogenation or by chemical reducing agents. The chemical reducing agent may be sodium or alcohol, Mendes reaction, or lithium aluminium hydride. Nitrile in presence of nickel and heat gives primary amine. N-butyronitride plus 2 moles of H2 gives N-butylamine in presence of nickel and temperature 433 Kelvin. Phenyl acetonitrile gives beta-phenyl ethylamine in presence of nickel and 433 Kelvin temperature. Nitrile themselves can be readily got from alkyl or ara-alkyl halides by reaction with sodium or potassium cyanide. Thus, an alkyl halide can be converted into a primary amine containing an additional carbon atom by first getting the nitrile from the halide or then reducing the nitrile. Alkyl halide NaCN and gives nitrile. Then further with reaction of H2, 2 moles of H2 and nickel, it give amine containing one carbon atom more than the parent alkyl halide. Third, reduction of oxyamines or amides. Reduction of oxyamines obtaining from aldehyde or ketone by reaction with sodium or potassium cyanide. Thus, an alkyl halide can be converted into a primary amine containing an additional carbon atom by first getting the nitrile from the halide and then reducing the nitrile. Alkyl halide in presence of NaCN give nitrile, then further gives amine containing one carbon atom more than the parent alkyl halide. Third, reduction of oxamines or amides. Reduction of oxamines obtained from aldehyde or ketone by reaction with hydroxylamine. The amide give primary amines in good yields. The reduction may be brought about chemically or catalytically. Aldoxamine in presence of NaC2H5OH give primary amine. Ketoxamine in presence of NaC2H5OH gives primary amine plus H2O, and amide gives primary amine in presence of LiAlH4H3O positive. Fourth, Gabriel phenylamide reaction. This is an important method for preparing of pure aliphatic or ara-alkyl primary amine. Phthalimide contain an amino group flanked by two carbonyl groups so that the hydrogen of amino group is acidic. Therefore, phthalimide can be easily converted into its potassium salt by treating with alcoholic potassium hydroxide. Potassium phthalimide on heating with alkyl or aryl halides or forms unsubstituted phthalamides. This is hydrolyzed to yield phthalic acid and a primary amine by heating with 20% hydrochloric acid under pressure or by refluxing with alkali solution. It is also possible to get primary amine from an alkyl phthalimide by their hydrogenation. In fact, this method is more convenient than the acidic or basic hydrolysis of phthalimide. Fifth, Hofmann-Bromide reaction. The treatment of bromine or chlorine in an alkaline solution of amide form an amines containing one carbon atom less than the starting amide. Amide plus Br2 plus 4 moles of KOH gives amine. For example, benzoate amine in presence of Br2 plus 4 moles of KOH give aniline plus K2CO3 plus 2 KBr plus H2O. Mechanism. The mechanism of the reaction have been subjected as much study as it involves an arrangement in the structure of the molecule. The hypobromite ion OBr negative generated by the alkaline solution of bromine or hypochlorite ion furnished by the alkaline solution of chlorine initiates the attack on the amide, which is followed by various other steps as summed up below. Fifth, step 1 involves the halogenation of amide to form an N-halimide. In step 2, the hydroxide ion abstract hydrogen ion from N-halimide. In step 3, the amine formed in step 2 undergo the anion formed in step 2 undergo loss of halide ion to give an unstable species containing an electron deficient nitrogen known as nitrene. This unstable species readily undergo 1,3 shift of alkyl or aryl group to nitrogen to yield an isocyanate. Step 4. It may be noted, however, the step 3 which involves the removal of halide ion ore and the step 4 which involves the actual rearrangement of molecular structure take place simultaneously. Finally, in step 5, the isocyanate get hydrolyzed to form an amine or carbonate ion. Evidence in favor of the mechanism. The above mechanism is strongly supported by the fact that the intermediates postulated in step 1, 2, 3 can actually isolated under stable conditions. These intermediate yields to accept product of Hofmann degradation on further treatment. It is also to be noted that the actual rearrangement in step 4 is in keeping with the journal pattern of 1-3-1-2 shift to electron deficient atom. The migration of group R along with the pair of electrons to nitrogen and their transfer of electron pair from nitrogen take place simultaneously. Therefore, this migration should occur with complete retention of configuration. This is found to be actual so by the studies of compound containing chiral carbon. It is also to be noted that methods 1-5 given above can be used for the preparation of primary amines only. 6. Reductive amination of aldehyde and ketone. Many aldehyde and ketone change into primary amines in reaction with hydrogen and ammonia at the temperature of about 373 Kelvin and 150 atm atmospheric pressure and in presence of a catalyst such as nickel. The reaction is also known as reductive amination. Mechanism. Reductive amination involves the formation of imines C double bond NH as an intermediate and proceeds through the following mechanism. Like ammonia, primary amines can also react with aldehyde or ketone to yield secondary amines. For example, benzaldehyde in presence of CH3NH2 and H2 or nickel gives methyl benzylamine. Similarly, secondary amines would react with aldehyde or ketone to furnish tertiary amines. For example, acetone gives an N-dimethyl isopropylamine. It may be noted, however, that the possibility of further reaction between aldehyde and ketones, the amines formed in a particular case, can be largely restricted by use of suitable proportions of the reactants. Note: both aliphatic and aromatic aldehyde or ketone can be subjected to reductive amination. Moreover, reductive amination of ketone gives rise to amines containing secondary alkyl group, as is obvious for the example cited above. The reduction amination can be employed for preparing a large variety of different classes of amines in a proper choice of reactants and their proportions. Apart from the method of preparing of amines given above, some other methods which are also used for the preparation of amines are given below. The methods are, however, not included in syllabus. 7th. Reaction with alkyl halide with ammonia. Monolysis. Simple or substituted alkyl halides, including aryl substituted alkene halides such as benzene CH2X, are converted into amine by treating with aqueous or alcoholic solution of ammonia. The reaction is usually carried out either by allowing the reaction mixture to stand at room temperature or by heating it under the pressure Hofmann's method. Ammonia is a nucleophilic reagent and displaces the halogen of alkyl halide to yield ultimately a mixture of primary, secondary, and tertiary amine, and even some quaternary ammonium halides as shown below. Primary amine, secondary amine, tertiary amine, quaternary ammonium salt. The third mechanism. Ammonia is a strong nucleophilic and attack the alkyl halide to a form of primary amine salt. The salt further undergo an equilibrium reaction with ammonia to give some free primary amines and ammonium salt reaction 1. The free primary amine is also nucleophilic and accordingly it attacks the halcyl halide to yield the salt of secondary amine, which is in equilibrium with the free secondary amine reaction 2. The secondary amine in turn react with halide to form the salt of tertiary amine in equilibrium with the free tertiary amine reaction 3. Finally, the tertiary amine also attacked alkyl halide to form a quaternary ammonium salt reaction 4. Thus, the reaction of ammonia with alkyl halide affords a mixture of salts of all the three types of amines together with some quaternary ammonium salt. From the mixture obtaining above, free amines are liberated by addition of alkyl and they are separated from each other either by fractional distillation or by chemical separation. It may be noted that first, even though ammonolysis of halide yield a mixture of products, primary amine can be obtained as a predominant product by using large excess of ammonia. For example, N-butyl bromide plus large excess of NH3 gives N-butylamine predominant product. Second, in place of using ammonia, if the initial reaction is brought about between alkyl halide and a large excess of primary amine aminolysis reaction, the main product formed is a secondary amine. For example, benzyl bromide plus large excess of CH3NH2 give methyl benzylamine. Third, similarly, aminolysis of allyl halide with excess of secondary amine yields mainly tertiary amine. For example, N-methylaniline plus CH3Cl gives N-dimethylaniline. Limitations of the reaction. Reaction of ammonia with halide suffer from some limitations as described below. A. The main disadvantage is that the reaction leads to the formation of mixture of amines as already explained. The separation of the mixture into individual amines is not quite easy. B. The reaction takes place readily only with aryl or aryl halides. Aryl halides, example halides in which the halogen atom is directly attached to the aromatic ring, are much less reactive toward nucleophilic reaction substitution. Accordingly, they form amines only if either the reaction is carried out under drastic conditions or the aromatic ring carry a strong electron withdrawing group such as NO2 group in ortho or para position to the halogen. For example, 2,4-dinitrochlorobenzene plus CH3NH2 gives N-methyl 2,4-dinitroaniline. The production of amine from aryl halide by nucleophilic substitution is always in competition with the elimination reaction. This is because the base ammonia can also be about dehydrogenation, leading to the formation of alkenes. The elimination reaction is particularly effective in case of tertiary aryl halide. For example, tertiary butyl bromide gives an 2-methylpropene. For example, tertiary butyl bromide gives 2-methylpropene. Therefore, tertiary halides are of little value in the preparation of amines. The best yield of amines are obtained by the use of primary halides, where substitution is the predominating reaction. 8th, ammonolysis of alcohols. When a mixture of an alcohol and ammonia is heated to about 630 Kelvin in a sealed tube in which the pressure of copper chromite or alumina catalyst is mixture of primary, secondary and tertiary amine is obtained. Uses of large excess of ammonia leads to the formation of primary amine as the main product. 9th, Curtius rearrangement. In this reaction, the aryl azide obtained by reaction between the acyl halide and sodium azide is heated in an inert solvent. As a result of acyl azide eliminates a molecule of nitrogen along with stimulate rearrangement to form alkyl isocyanate, which upon hydrolysis give a primary amine. Mechanism. Curtius rearrangement takes place as follows. Schmitt rearrangement. This is modified form of Curtius rearrangement. Here the acyl azide are obtained by reaction between a carboxylic acid and hydrozonic acid HN3 in the presence of concentrated sulfuric acid. The acyl azide is allowed to undergo further reaction in situ without actual isolating it. 10th, reduction of N-alkyl amide and NN disubstituted amides. Catalytic or chemical reduction of N-alkyl amide give rise to secondary amines. N-alkyl amide in presence of LiAlH4 and H3O positive gives secondary amine. Similarly, reduction of N disubstituted amide with LiAlH4 yields to tertiary amines. N disubstituted amide in presence of LiAlH4 and H3O positive give tertiary amine, where R, R dash and R triple dash in N disubstituted amide may be same or different. 11th, hydrolysis of para-nitrosodioalkyl aniline. A very suitable method for the preparation of secondary amine is to carry out the hydrolysis of para-nitrosodioalkyl aniline. Para-nitrosodioalkyl aniline is itself obtained from aniline by N dialkylation followed by reaction of nitrous acid. Aniline in presence of 2Rx and -2X, 2 moles of HX gives N-dialkyl aniline. Further reaction with HNO2 gives para-nitroso N-dialkyl aniline. Further reaction with H2O or NaOH gives para-nitrosophenol plus secondary amine. 12th, decomposition of quaternary ammonium hydroxide. The best method for preparing tertiary amine is by decomposition quaternary amine hydroxide by strongly heating. Quaternary ammonium hydroxide themselves are obtained by the hydrolysis of quaternary ammonium salt by hydrolysis with most silver oxide. Quaternary ammonium salt plus most silver oxide gives quaternary ammonium hydroxide. Further on heat gives tertiary amine plus alcohol plus AgH. Separation of primary, secondary and tertiary amines. As described above, certain method of preparing amine leads to the formation of mixture of primary, secondary and tertiary amines and quaternary ammonium salt. When a mixture of amines or of salt, amine and quaternary ammonium salt is to be separated, it is first distilled with potassium hydroxide. The quaternary ammonium salt, being not volatile, is left behind while the mixture of amine distills over. The mixture is then separated by the following method. First, fractional distillation. This method is generally employed on an industrial scale. The mixture of amines is fractionally distilled by employing highly effective fractionating apparatus. 12th, Hofmann method. The mixture of amines is treated with diethyl oxalate. When primary amine form a substituted oxamide, a solid, the secondary amine form a dialkyl oxamic ester, a liquid, and the tertiary amine does not react. Regeneration of amines. On distilling the reaction mixture, the tertiary amine distills over first and it collected as the distillates. The remaining mixture is cooled and filtered with oxamic ester passes as the filtrate and oxamide is left as an residue. Oxamide and oxamic esters are now separately boiled with alkali to get back the original amines. Third, Hinsberg method. The mixture of amines is treated with paratoluene sulfonyl chloride, as also known as thiazole chloride (TSCl), or Hinsberg reagent. In the earlier days, benzene sulfonyl chloride was used as Hinsberg reagent and in presence of sodium hydroxide. The primary amine forms monoalkyl sulfonidamide, which dissolves in sodium hydroxide with the formation of sodium salt. Paratoluene sulfonyl chloride plus primary amines gives an alkyl sulfonidamide with -HCl. And further on reaction with NaOH gives sodium salt of an alkyl sulfonidamide soluble. The secondary amine form dialkyl sulfide, which is insoluble in alkaline. The tertiary amine does not react at all. The regeneration of amines, the alkaline mixture obtained above, is accepted with either when the unreactive tertiary amines is and sulfomide of tertiary amine pass into ether layer, while the sodium salt of sulfonidamide is of primary amine remain in aqueous layer. Melting and boiling point of some amines are shown in this table. Melting point of methylamine is shown 181 Kelvin and boiling point is 265.5 Kelvin. Further, the other melting and boiling points of some amines are also shown below. For example, dimethylamine, tertiarymethylamine, ethylamine, diethylamine, triethylamine, N-propylamine, isopropylamine, benzylamine, aniline, N-methylaniline, N-dimethylaniline, orthotoluidine, metatoluidine, paratoluidine, diphenylamine, triphenylamine. Chemical properties of amines. The chemical properties of amines closely resembles to those of ammonia and are largely determined by the presence of lone pair of electrons on the nitrogen atom. The important properties are discussed below. First is basic character. Like ammonia, all the classes of amines have a lone pair of electrons on the nitrogen atom. Since their pair of electrons is available for being shared by atom which may have electron poor, amines react as bases, so they undergo the following reaction. In the reaction of amines, only electrophilic aromatic substitution in aryl amines and reaction of amines with nitrous acid are included. Formation of hydroxides. Like ammonia, the water-soluble amines are substituted ammonium hydroxides, which ionizes to furnish hydroxyl anion. Naturally, the aqueous solution of amine are basic in nature. Second, formation of salt. Being basic in nature, amine react with acid to form salts called amine salt. As the amines are weak bases than hydroxide ions, the salts are readily converted back into free amines by aqueous hydroxide. The relative basicities of amines and effect of substituent on basicity are discussed a little later. Salts of amines with inorganic acid are soluble in water but insoluble in ether. This property is made use of in removal of non-basic impurities from amines. The crude amines is treated with an acid, say dilute hydrochloric acid. When the amine changes into water-soluble hydrochloride, the non-basic impurities, which are usually soluble in ether, are then removed from the aqueous acidic mixture by excretion with ether, while the amine salt is left behind the aqueous layer. From the aqueous layer, amylines is regenerated by basification. Salts of amine with organic acid such as oxalic acid, tartric acid, and picric acid are soluble in water as well as organic solvents. Therefore, they can be easily obtained in pure stable state by recrystallization from organic solvents. As such, they are often employed from the identification of amines. Mention must also be made of the salts known as chloroplantanes obtaining from the treatment of amines with chloroplatanic acid H2PtCl6. The salts are insoluble in water and have been used in the determination of equivalent and molecular weight of amines. Reaction with metal amines. Due to the ability of lone pair electrons on nitrogen, amines also act as ligands to form soluble coordinate complexes with transition metal ions such as Ag positive and Ce2 positive ion. For example, silver chloride dissolved in methylamine to form a soluble complex. Similarly, ethylamine react with copper salt to give a deep blue color complex. Third, alkylation. All the classes of amines undergo alkylation on treatment with alkyl halide. The starting amine first changes into amine and next higher class was which ultimately changes into an quaternary ammonium halide. The process of converting an amine into quaternary amine salt through reaction with alkyl halide often refers to an exhaustive alkylation. If the halide used in some methyl halide, usually methyl iodide, the process is termed as exhaustive methylation. It is obvious that the exhaustive methylation, a primary amine would take up 3 methyl groups, a secondary amine will take up 2, and a tertiary amine will take up only 1 methyl group. The mechanism of the reaction involves the nucleophilic attack of amines and on the alkyl halide. The amine can be alkylated but may be aliphatic or aromatic, but the halide is usually in an alkyl halide. Fourth, conversion into amides. Acylation. Primary and secondary amines but not tertiary amines react with an acid chloride or acid anhydride to give an substituted amide. The reaction is also referred as acylation of amine. In case of amines or the basic acid chlorides and anhydride is aromatic, the reaction is generally carried out in the presence of base such as aqueous sodium hydroxide or pyridine. It is called Scotman-Bowman reaction. Mechanism. The mechanism of the reaction involves the addition of nucleophilic nitrogen of the amine to the acyl carbon. This is followed by the elimination of chloride ion and H positive ion to form a substituted amide. Tertiary amine too can also act as a nucleophilic reagent in attacking the acid chloride and anhydride, but the addition compound cannot lose H positive ion to form a stabilized product, hence no reaction takes place in this case. The process of acylation is often employed for the identification of primary and secondary amine. This is because the acyl derivatives, particularly acetyls or benzoyl derivative of both primary and secondary amines, are generally crystalline compounds having sharp melting point. Fifth, conversion into sulfonamides. Primary and secondary amines also react with sulfonyl chlorides such as benzene sulfonyl chloride, Hinsberg reagent, and para-toluene sulfonyl chlorides to form substituted sulfoamides. For example, the conversion of amine into sulfonide amide forms the basis of the chemical method of separating the different classes of amines from each other. It is also used for determining the class to which a group amine belongs. Sixth, reaction with the nitrous acid. The tertiary class of amine react differently with nitrous acid, which is generally obtained in situ by the action of mineral acid on sodium nitrate, as illustrated below. Primary aromatic amines react with nitrous acid in a cold to yield diazomium salts. This reaction is known as dissociation. Primary aromatic amines gives a diazomium salt. The aromatic diazomium salts are sufficiently stable in a cold aqueous solution to enable them to be used as important intermediates in many synthetic processes. Primary aliphatic amines also react with the cold nitrous acid to yield diazomium salt, but aliphatic diazomium salts are unstable even in the cold and decompose as soon as they form to yield a complex mixture to different products. It is obvious from above that reaction with nitrous acid can be used to determine if the amine is primary, secondary or tertiary amine, or in some cases if the amine is an aliphatic or aromatic amine. Seventh, carbonyl amine reaction. When a primary amine is warmed with chloroform and alcoholic potash, an aryl isocyanide or carbyl amine is formed, which gave a very offensive smell. Since the reaction is not given by secondary and tertiary amine, it is used for distinguishing primary amines from other classes of amines. The mechanism. The reaction is believed to take place as given below. Eighth, action of carbon disulfide. When warmed with CS2 in presence of mercuric chloride, aliphatic primary amine yields isothiocyanide, which smell like mustard oil. This reaction is known as Hofmann mustard oil reaction and can also be used for identification of primary amines. On the other hand, when an aromatic primary amine such as aniline is heated with CS2 and solid KOH, it gives an diphenylurea, which forms phenyl isothiocyanide on treatment with concentrated HCl. Ninth, reaction with aldehyde and ketone. Primary amine react with aldehyde and ketone to form amines known as chief bases or aniles. For example, benzaldehyde plus aniline give benzaldehyde aniline. Such if base's own reduction give rise to secondary amines. For example, such if base gives ethyl methylamine with own reduction with Ni. Secondary amines react with aldehyde and ketone containing alpha hydrogen atom to form carbonyl amines, which are highly unstable and readily undergo dehydration to form enamines. 10th, acidic nature. Even though amines are essentially basic in nature, primary and secondary amines can also behave a acid when react with alkali metal or Grignard reagent. For example, primary amine gives 2RH negative Na positive plus H2. The tertiary amines do not undergo these reactions because they do not contain any alpha hydrogen attached to nitrogen. 11th, oxidation. All classes of amines are readily oxidized, but the nature of the product formed depend upon the starting amines and the oxidizing agent employed. The oxidation can brought about a variety of oxidation reduction such as H2O2, pre-oxy acid and caro acid H2SO5. Primary and secondary aliphatic amine usually give complex mixture on oxidation, but tertiary amine are cleanly oxidized to tetraarylamine oxide. In case of aryl amines, the oxidation is not confined to amino group but also take place in ring. For example, aniline plus controlled H2K2 Cr2O7 H2SO4 give benzoquinone. 12th, electrophilic aromatic substitution in aryl amine. In addition to the chemical properties of the amino group discussed above, the ring of aryl amine can undergo the typical electrophilic aromatic substitution reaction, which involve carbocations as intermediates. In these reactions, the NH2, NHR, and NR2 groups act as strongly activating and ortho-para directing groups. This is because the lone pair of unshared electrons of the nitrogen of these groups enables these groups to donate electrons by resonance mechanism. During electrophilic aromatic substitution of benzene itself, the carbocations intermediates formed by the attack of electrophile is a resonance hybrid of their contributing structures as shown below. But when benzene ring containing NH2, NHR and NR2 group attached to it undergo electrophilic attack, the intermediate carbocation formed can have additional contribution structures. The structures such as first in case of attack of ortho position and two in case of attack of para position and are formed by resonance interactions of lone pair of electrons on nitrogen with the benzene ring. It may be seen that these structures are particularly stable since in every atom except hydrogen, which cannot of course have more than 2 electrons, has a complete octet of electrons. The formation of additional contributing structures leads to the stabilization of intermediate carbocation and increases its ease for formation. As a result, ring substitution in aromatic amines occurs very rapidly and preferably to ortho and para position. It may be accompanied by even side reaction. Production of amino group. It is sometimes necessary to decrease the speed of reaction or to prevent the formation of side product by acetylation of the amino group before introducing a substituent into the ring. The acetylated amino group NHCOCH3 is also activating and ortho-para directing but much less powerful than the free amino group. This is due to the fact that oxygen is of the carbonyl group stands to withdraw the unshared pair of electrons on nitrogen toward itself and thus make the pair less available for donation to the aromatic ring. As such, the ring is not strongly activated. Therefore, the protection of amino group by acetylation can be used to control the rate of electrophilic substitution and prevent the occurrence of side reaction. First, halogenation. Halogenation of aromatic amines proceeds to a very fast rate and also available ortho and para position get halogenated even in the presence of a catalyst. This aniline on treatment with aqueous solution of bromine readily forms 2,4,6 tribromoaniline. If a monohalogen derivative is desired from the amino group is first acetylated and then the ring is halogenated. After the halogenation, the parent amino group is regenerated by hydrolysis of the substituted amide to get the substituted amine. Second, nitration. Direct nitration of aromatic amine is not feasible process due to the following reasons. First, direct nitration results in the formation of oxidation product in addition to the desired nitro compound. This is because nitric acid of the nitrating mixture is not only a nitrating agent but also an oxidizing agent, and the highly activating benzene ring can easily get oxidized. The considerable amount of amine would be lost by oxidation. Second, even though amino groups is orthopara directing, the direct nitration result in the formation of mixture of meta and para derivatives. It is believed that in a strongly acidic solution, the amines are converted into anilinium. In the anilinium ion, the nitrogen has no longer got an unshared pair of electrons but has a positive charge and such directs to a large percentage of entering groups to the meta position. In view of the reasons given above, nitration is best carried out using a acetylated amines rather than the free amines. Acetylation lowers the reactivity of aromatic ring and thus prevents the formation of oxides product. At the same time, acetylated amino group leads to the formation of product having the substituent in the ortho and para position only. Thus we have aniline gives acetaldehyde, gives para-nitroacetylidene, main product plus para-nitroaniline. Sulfonation. In spite of the presence of strongly activating amino group, the sulfonation of aromatic amine take place under rather drastic conditions. For instance, aniline get sulfonated only when heated at 453 to 463 Kelvin for 4 to 5 hours with concentrated sulfuric acid, para-aminobenzene, sulfonic acid commonly called sulfonic acid being the main product. The process is known as baking and take place by the amine salt anilinium hydrogen sulfide in this case. The use of strong reaction conditions can be explained in terms of the fact that amine is free converted into anilinium salt. The salt contains N positive H3 group which with an electron attracting and therefore have a deactivating influence on the ring. In the case, however, the main product may be accepted to be meta isomer and not para. The predomination formation of para product is justified by pointing out the sulfonation. Unlike other substitution reactions, it is reversible in nature. Accordingly to the formation of the product is determined by the position of equilibrium and not the relative rates of the formation of the different isomers. It appears to the equilibrium favors the para isomer because of the most stable isomer. It is also quite possible that sulfonation of amine may involve some mechanism which is entirely different from that of other aromatic substitution reaction. Zwitter ion structure. It may be noted that aminosulfonic acids such as sulfonic acid contain both an acidic and a basic group. Therefore, it would not accepted in these groups reacted to form an intramolecular salts. The sulfonic acid exists largely in the form of an internal salt in which the hydrogen ion forms the sulfonic acid group have been taken up by the amino group. This type of internal salt is known as dipolar or Zwitter ion. Supporting evidences: the Zwitter ion structure of sulfonic acid implies the absence of free amino or sulfonic acid groups in its molecule. This is supported by its properties. First, sulfonic acid decomposes with melting point at 553 Kelvin to 573 Kelvin, while benzene sulfonic acid having a free sulfonic acid group and aniline having a free amino group melt only at 339 Kelvin and 268 Kelvin respectively. Second, sulfonic acid is almost insoluble in water as well as most organic solvents. In contrast to this, sulfonic acid are generally highly soluble in water, while amines are generally soluble in other organic solvent. Third is sulfuric acid is insoluble in aqueous mineral acid where amines go into solution with the formation of salts. Sulfonic acid, however, dissolves in aqueous base such as NaOH. This is because the strongly basic hydroxide ion can abstract a proton from NH3 to form the water-soluble sodium salt. Explanation of relative basicity. Explanation of relative basicity. The basicity of amines depend upon the ability of electron pair on nitrogen atom and the stability of the substituted ammonium ion formed. As such, an factor that can increase the ability of electron pair on nitrogen or increase the stability of ammonium ion relative to the parent amine will increase the basicity of amines. On the other hand, any factor that has the opposite effect will decrease the basicity. Aliphatic amines. Greater basicity of aliphatic amines as compared to ammonia. First is inductive effect. The greater basicity of aliphatic amines as compared to the ammonia can be explained in terms of electron releasing inductive effect of alkyl group. Aliphatic amine contain one or more allyl group in place of hydrogen atom of ammonia. Now an alkyl group being electron releasing increase the electron density of nitrogen and thus make the electron pair of nitrogen more available for sharing. At the same time, the electron releasing inductive effect of alkyl group increases the positive charge of the substituted ammonia ion formed by the amine and thus increase the stability. R helps to increase the electron density around nitrogen and thus makes the electron pair more available. R disperses the positive charge of the ion and thus increases its stability. It may be noted that due to the inductive effect alone, a tertiary amine should be more basic than a secondary amine, which is in turn should be more basic than a primary amine, while secondary amines are invariably found to be stronger bases than primary amines. The tertiary amines have been found to be weaker than secondary amine and sometimes even weaker than primary amines as in evident for the observed order of the following cases. This means the relative basicity of primary, secondary and tertiary amines cannot be explained in terms of electronic factors alone. There are other factors, particularly solvation effect, which also play their role as explained below. Second, solvation effect. This is another factor which strongly influences the basicity of amines. In aqueous solution, the substituted ammonium ion formed by the amines by taking up the proton in highly solvated in water, hydrogen bonding and are therefore strongly stabilized, but the extent of solvation and consequent stabilization depends upon the number of hydrogen atoms in substituted ammonium which can form hydrogen bond as shown below. Substituted ammonium ion from primary amine maximum stability to solvation. Substituted ammonium ion from secondary amine. Substituted ammonium ion from tertiary amine. minimum stabilization of solution. As the number of hydrogen atom on substitution ion formed goes on decreasing in from primary to tertiary, the extent of hydrogen bonding of the stabilization of the ions by solution also decreases.